Welcome to Chapter 19, Statistical Process Control. One of the areas where statistics has become the largest impact in business world is in the area of quality. Quality movement comprises much more than just statistical or quantitative methods. However, a large part of success of the quality movement is due to the increased use of quantitative methods. One set quantitative tool is referred to as Statistical Process Control, or SPC. Its two most important goals can be summarized as: get it right the first time is much better to catch mistakes early when they are less costly to fix than wait for final inspection. Reduce variation. Variability is the main culprit that hurts quality, so companies need to be able to measure it and give workers a way to eliminate it. W. Edward Deming is probably more responsible for today's emphasis on quality than any other single individual. Deming taught the Japanese industries after World War II the principles of quality management, for which they are known for. In the early 80s, Deming and a few other quality gurus began teaching U.S. companies the statistical principles they need to compete successfully. Deming is perhaps best remembered for his 14 famous points, a list of precepts he taught in all seminars. 14 points. Consistency of purpose. Create consistency of purpose towards improvement and product and service, allocating resources to provide long-range needs rather than only short-term goals. Profitability with a plan to become competitive, stay in business, and provide jobs. The new philosophy. Adopt the new philosophy. We are in a new economic age created in Japan. We can no longer live with commonly accepted levels of delays, mistakes, defective material, and even defective workmanship. Transformation of Western management style is necessary to halt the continued decline of an industry. Cease dependence on mass inspection. Eliminate the need for mass inspection as a way to achieve quality by building quality into the product in the first place. Require statistical evidence of the built-in quality in both manufacturing and purchase functions. End lowest tender contracts. End the practice of awarding business solely on price tag alone. Improve every process. Improve constantly and forever the systems of production and service to improve quality and productivity and thus constantly decrease costs. Institute training. Institute modern methods of training for everyone's job, including management, to make better use of every employee. Institute the leadership of people. Adopt the institute leadership aimed at helping people do better job. Drive out fear. Encourage effective two-way communication and other means to drive out fear throughout the organization so that everyone can work effectively and more productively for the company. Break down barriers between departments and staff. Eliminate exhortants. Eliminate the use of slogans, posters, and exhortants of the workforce, demanding zero defects, a new level of productivity without providing method. Eliminate arbitrary numerical targets. Eliminate work standards that prescribe quotas for workforce and numerical goals for people in management. Promote pride of workmanship. Remove barriers that rob hourly workers and people in management of the right pride. Encourage education. Institute a vigorous program of education and encourage self-improvement for everyone. Top management's commitment and action. Clearly define top management's permanent commitment to ever improving quality and productivity and their obligations to implement all these principles. Introduction to control charts. Control charts are one of the most important statistical tools available for reducing variability and improving quality. They are generally easy to use and they provide a wealth of information about a process. There are two types of variability in a process: If the current variability is output of the process is due to entirely inherent nature of the process, we say that the variability is due to common causes, and the process is in statistical control or simply in control process. Common causes of variability is inherent variation in an in-control process. A sum of the current variability of the process is due to specifically assignable cause such as bad material or improper adjustment machine. We say the process is out of control. Assignable cause variability is the extra variation observed when a process goes out of control, which can be for any number of reasons. One of the main purposes of the control chart is to monitor the process so the company can see when a process goes from an in-control condition to an out-of-control condition. A process of in-control is not necessarily a good process, but at least it's predictable regardless of whether it's good or not. An out-of-control process, on the other hand, is unpredictable. The assignability cause that produces out-of-control behavior can often be corrected by workers on the shop floor without management intervention. There is little workers can do to improve an in-control process that has unacceptable variability. Control chart allows workers to measure the amount of variability, but is generally no way they can reduce the amount of variability without the guidance for management. Primary reason control charts have become so popular: they improve productivity and lower cost. Productivity is defined as the number of goods items produced per hour. Control charts allow mistakes to be found early in the process before the result is poorly finished product. They prevent unnecessary process adjustments. Control charts allow the operator to see the process is really in need of an adjustment. This prevents unnecessary tampering. They provide diagnostics information about the process. Control charts not only signal when something's wrong, but they also provide clues to the cause of the problem. They provide information about the process capability. Process capability is defined as the ability to produce outputs that meet specific specifications. Control charts provide this information at least when the process is in control. There are two basic types of control charts. Charts for variable are relevant when there is a measurable quantity such as a diameter or a weight that can be monitored. The purpose of the chart is to see how the quantity varies through time. Charts for attributes are appropriate when an item is judged to conform to specification or not. This type of chart is proportionally conforming or non-conforming parts. It's also appropriate for tracking the number of defects through time. Two of the most common types of variable control charts are the X-bar chart and the R chart. The X-bar and R charts we randomly sample a small number of items and measure the characteristics. The result of the sampling is a subsample. The X-bar chart plots the average of the small subsample through time. Its purpose is to see how the mean of the process is changing through time. The R chart plots the ranges maximum, minimum, minus minimum, a small subsample. Purpose is to see the variability. The resulting time series plots of the information when center lines and control limits are added to the charts. A center line indicates that the average value of the X-bar R chart vary around. Control limits place upper and low bounds where the X bars or the R's should be in process control. Measuring the volumes of soda cans. To use the X-bar R chart to check whether process of filling soda cans is performing as it should. Solution. The data file contains data on the number of ounces of soda it can label 12-ounce cans. Every half hour, 5 cans of soda from the production process was measured for fill volume. They were done for 70 consecutive half-hour periods. To create the chart in Stat Tools, designate the chart range in the Stat Tools area, select the XR chart for the quality group, fill out the resulting dialog box, variables, and so on. As you can see, this is what it looks like. The X-bar chart for Stat Tools creates the R chart, which continues. These charts are shown below. No points are outside control limits. There's no obvious non-random things. Therefore, the process appears to be in control. More on the X-bar and R chart. The X-bar chart is a subsample of averages that is an individual X-bars. The center line for this plot of the average of all X-bars and X double bar, the lower and upper control limits denote lower control LCL and UCL, are appropriately 3 standard deviation on either side of this, where the standard deviations of X bar is the sigma square root of the number, and n is the subsample. The R chart measures within the subsample variation over time. Each R measures the variability in the process at a given point. For the R chart, we use the average, R bar, the center line, and again. We typically look at the R chart first because the control limits for that. Assuming the R chart objective to continue the X-bar R chart to learn whether soda process is in control or not. Solution: a plot of the subsamples base the control limits on this. The resulting X-bar is as shown. The R chart shows the process stayed in control for at least 10 or more and a half hours. However, beginning shortly after sample 40, the process variability appears to have increased in the 2 points fixed around. About the same time, the X-bar suggests a downward shift in the process mean. Many points are below the center line and the final crosses the lower limit. It appears that this machine needs to be readjusted to bring the mean back in. After the previous control chart should be indicated the in control process. As we monitor the process with control charts, there are 2 types of errors that we can make. A type 1 error occurs when we react to an out-of-control indication with the fact the process is still in control. We call this a false alarm. We want to make the probability of type 1 very small. If it's too large, we react too many times to false alarm. Therefore, we set the control limits fairly far apart so that a chance of observing out beyond that the mean of the subsamples until and in control. Type 2 error occurs when the process has gone out of control, but the control charts do not indicate it. It's difficult to calculate the probability of a type 2 error because there are many types of out of control conditions that could occur. To keep both types 1 and 2 errors to a minimum, there are 2 suggestions. Sample more frequently, increase the subsample size. Both strategies are intended to decrease the out of control process. In addition to the points beyond the control limits, there's possible indirection of out of control process. At least 8 upward or downward consecutive changes, at least 8 consecutive points above or below the center line, at least 2 of 3 consecutive points beyond 2 standard deviations from the center line, where they are both on the same side of the center line, usually applied only to the X-bar chart. at least 4 or 5 consecutive points beyond one standard deviation from the center line, where all 4 of the same sides of the center line usually applied only by the X-bar chart. Other out-of-control indications. For the last 2 conditions, it is common to divide the region between the center lines into control limits into 3 zones. The condition 3 is zone A rule, and condition 4 is zone B. The idea is that although the points within the zone A or B are within control limit, it is likely their in-control process would be nearly as many points. The small number of observations taken periodically should be rational subsamples. This means that they should be taken in such a way that only common cause variabilities can be attributed to the points in a particular subsample. There should not be any assignable cause of the variabilities that affects some of the points in the subsample. Typically, rational subsamples are obtained by taking observations nearby in time. To see how non-rational samples can be produced misleading information, X-bar R chart. 2 parallel production machines produce identical types of gaskets. Every 15 minutes, 4 gaskets sampled, 2 from each machine to determine their thickness. The data contains here. The chart for these data appears below. The X-bar R chart looks too good. Each X-bar is an example of 2 typical machines, 1 observation and 2 typical machine observation. With such samples, the high tends to cancel the lows. The rational subsample philosophy would suggest that control charts for each machine, as shown below here. There is one out of control point on the X-bar near the other. Machine 2 should be checked for assignable causes. Deming's funnel experiment and tampering. If a system is already in control, frequently small adjustments can actually make it worse. Deming called this tampering. Deming placed the funnel on the target on the floor and dropped a small ball through the funnel, attempt to hit the target. Deming proposed 4 rules for adjustment position. Never move the funnel. After each ball is dropped, move the funnel relative to its previous position and compensate for error. Move the funnel relative to its original position of 0, 0 to compensate for error. Always reposition the funnel directly over the last drop. We can see these rules by running a simulation in Excel. The following equation allows us to simulate 50 consecutive drops for any 4 rules, where pxt and pyt are the x and y coordinates for the position of the funnel before the drop. The figure on the bottom left illustrates the simulation for Rule 2. After implementing each of the 4 rules for 50 drops, we can use the data table to show at the bottom right to replicate of 100 times the distance from the 50th drop to the target. Because we want these distances to be small, Rule 1 is performing best, with the Rule 2 following very closely behind, 3 and 4 performing terribly. As Deming predicted, tampering with an in-control process never helps, and it can have negative effects. Control charts in the service industry. Although most applications of control charts are in the manufacturing area, it's certainly possible to apply the same analysis to problems in the service industry as shown in the next example. Measuring the timeliness of a check process. To see how control charts can help Woodstock find their reasons for untimely check processing, and suggest ways to decrease check processing. Solution: Woodstock Company is having difficult processing checks in a timely manner, which is making the suppliers unhappy and keeping Woodstock from obtaining the discount many suppliers offer for prompt payments. To produce control charts, assume that Woodstock measures the process times for 5 checks completely each day. Each processing is defined as the time from when the supplier shipment is received until Woodstock sends the check to the supplier. The data file contains these processing times for 60 consecutive business days. The X-bar chart below indicates out-of-control points on day 7 and 10. Woodstock learned that on day 7 and 10, people in finance implemented change in the check preparation process, but the check change backfired and was eliminated 5 days later. Woodstock eliminated points 7 and 11 and formed the new checks that showed statistical control, but it's still alarmed at the high average of processing times and high variabilities. Management then discovered several unnecessary checks in the preparation process and took steps to streamline. The X-bar chart through day 60 with 7 eliminated appeared below. The R chart indicates the lower level of variability, and the X bar indicates the decrease in the average time. Control charts from attributes. An item that failed to conform to specifications is called a non-conforming or defect item. When items can be classified only as conforming or non-conforming, we typically chart the proportion that they are conforming during a consecutive period. The resulting chart is a P chart. It is one of the several types of control charts, attribute charts, where the term attribute indicated as on or off type of measurement. The item has either the attribute or it doesn't. The other types of attribute charts are called C charts or U charts that are used to chart the number of rate of defects and successive items that are flaw. These charts are formed easily with the stat tool. The P chart, suppose we want to sample N item during a period and K of these failed items. The P chart is then a time series of PIS. It's plot the proportion of items that are non-conforming defective through time. We place a center line and the control limits in the chart in such a way that the PIS for the in-control process varies randomly around the center line and almost never crosses the limits. The lower chart, 3 standard deviation below the chart center line, where the center line is proportionally of all items that are non-conforming. Measuring the proportion of defective chips. Objective: to use charts to see whether the chip manufacturer process at the SoundTech is in control in the process of small number of non-conforming chips. Solution: SoundTech manufactures electronic chips for sound systems and personal computers. Each chip is classified as non-conforming or conforming or non-conforming. Each has 75 chips are tested for the conformance. The data file lists the number of non-conforming chips out of the 75 for 25 consecutive hours. To create a P chart, select the P chart from Stat Tool Quality Process Group. In the dialog box, the variable numbers of non-conforming and sampling size should be selected. The P chart appears below. The current process appears in control, but average percentage non-conforming of the 25 is not good. SoundTech will verify. The red bead experiment. Deming often used the following red bead experiment to illustrate the system only common cause variation. Some workers are bound to do the best on some days and worst on others for no particular reason. It also illustrates all workers can fail to live up to the standard through no fault of their own, if the system is not designed correctly. The experiment is very simple. There's a large container of beads. 20% are red, 80% are white. Red beads correspond to defective. Several people are asked to play the role of the worker, and the others are asked to help out as inspector. Each worker gets a paddle with 50 holes, where each hole can hold exactly one bead. Each worker must put their paddle into the container and pull out the exact 50 beads, which is one day's production quality. Each person to do the job, no more than 2 defectives per each. Obviously, the experiment is stacked against the worker. Process capability. When we analyze whether a process is able to meet set specification, it is called a process capability analysis. Process capability measures the ability of an in-control process to produce the item that met specification. In the process capability analysis, we are typically given a lower and upper specification, denotes LSL and USL. And we want to calculate the proportion of outputs from a given process that fall within these limits. Based on the data generated from the process, we perform the probability calculation to see how capable the current process is, keeping within the specifications. To use control charts to check whether the manufacturing process is in control, and to use standard statistical procedures to estimate the proportion of rods that meet spec. Solution. Manufacturing process produces rods for a mechanical device. Engineers have determined that the diameter of the rods must be between 20.8 and 20.95 millimeters. Diameters of 6 randomly selected rods were measured every half hour for several production shifts, and the data are calculated. First, examine the X bar R chart to see whether the current process is in control. The X bar to the right shows that the process is in control. Once it's determined that the process is in control, estimate the proportion of rods that fall within the specification limits. Count the number of observed rods with the diameters within the limits. The proportion is 266 or 0.985. Create the probability of the models. First, verify that all rod diameters are normally distributed by creating a histogram of rod lengths. The histogram indicates reasonable bell-shaped distribution of diameter, so normal probability models reasonable. The use of the norm dist function calculates the probability below the LSL and the USL as shown to the right. Therefore, it's almost no probability of being below the LSL, but there's a probability of being USL just below. Slightly more than 98% of the rods should meet specification if the process continues the current operating. Finally, project the results to large numbers of items. Multiply each of the probabilities by 1,000,000, almost 20,000 parts per million. We have a fail rate of 83 parts per million, which will fall below that. Process capability index. If the output from an in-control process are approximately normal distributed with the mu, mean U, and standard deviation sigma, then we know that almost all of the items produced will be within 3 standard deviations of the mean. This interval has a length of 6 sigma, but we want the items to be within the interval of the lower and upper standard levels, so we subtract them. One way to judge the capability of a process is to compare the length of these two intervals with a process capability index. The capability index is defined by the equation. To understand C, assume that the ideal output value called the target is halfway between. Also assume that the current process U of the process is equal to the target and that the distance between is 3 sigma. When the target is midway between the specification limits, the process mean is equal to the target and the process normally distributed. it can be shown that the probability of falling outside the specification, where Z is normal with the mean of that. We use this equation to show the parts per million outside the specification decrease as this process increases. If there is variation in a process and the process mean is off target, we need the slightly different capability index denoted by C, P, K to measure how close the process mean is to the nearest specification. If the CPK is unacceptably small, there are two possibilities. Try the center of the process by adjusting the process mean to the target. In this case, the CP and the CPK coincide. Try to reduce the process variation with or without a shift in the mean. By reducing the sigma, we automatically reduce the CPK and the CP, regardless of whether the mean is on target. Both the CP and CPK are simple indexes of the process capability. The larger they are, the more the process capable the process is. The equivalent description measure of the number of sigmas of the process. A K sigma process is one in which the distance from the process mean to the nearest specification limit of K sigma, where sigma is the standard deviation. Summary. The CP index is appropriate for the process in which the mean is equal to the target. Process with the CP equals 1 produces about 2,700 out of specification items per million, but this number decreases dramatically as the CP increases. The CPK index is appropriate for all processes, but it is especially useful when mean is off target. Processes with CPK equal 1 produce about 1,300 out of specification per million on the nearest side, and fewer on the other. Again, the number decreases dramatically as the CPKs increase. Both the CP and CPK are only indexes of process capability. However, they imply the probability of beyond the specification. The 3 sigma process, CPK equals 1, whereas 6 sigma process has a CPK of 2. In general, that distance quality improves dramatically as that increases. Till the 1990s, most companies were content to achieve a 3 sigma process. This is CP of 1. Moral question the wisdom on this on 2 counts. Products are made of many parts. The probability that a product is acceptable and the probability that all parts making the product are acceptable. When using control charts to monitor quality of the 1.5 standard deviation or less in the process, this detect. Given the process mean might be as far as 1 point from this target and the product is made up of many parts, 3 sigma process is not a good. Following analysis refer to the standard sigma analysis. So the product is composed of m parts. Calculate the probability that all m parts are within the specification when the process mean is above 1.5 sigma, above the target and the distance from that. Use this equation where z is normal and the standard deviation is 1. We can easily implement this in Excel as shown below. This figure shows that the 3 sigma process, row 13, is not great. In contrast, a 6 sigma process, row 16, with only 0.34 of the 1,000 products produced, no wonder Mueller goals which were 6 sigma were capability where everything was right. End of chapter 19. Thank you.